Hello. The next topic we're going to discuss is transformer. Okay, and here's the original research paper. The title is "Attention all you need." That is because in transformer there's a very important structure called attention, and they use attention to analyze the sequence data. Okay, so we have some explanation right here, but I would like to what I would like to show you is the figure in this paper. Okay, so let's first take a look at this one. Okay, first I will talk about what is attention. Okay, so basically, when we try to analyze the sequence data or the text, okay, one of the way is to use recurrent neural network, because recurrent neural network can accept a lot of input sequence, right? And the passed information will be passed from the left hand side cell to the right hand side, and so on and so forth and so forth. So basically, it's very similar to human beings to read text from left hand side to right hand side. So recurrent neural network is one of the way to analyze sequence data or text-based data. But however, we mentioned it before that it is a little bit difficult for recurrent neural network structure to pass a very long information from the very first beginning to the later cells. So some information will be lost when you pass the information through state, or say edge vector. So after that, and another reason we don't use recurrent neural network to analyze text is that recurrent neural network need more computation power to analyze data, because all the information should be passed from the left hand side to the right hand side. So you cannot do parallel computing, because for the later cell, the information is not there yet. So you have to pass the information step by step, cell by cell, so that computation would be a little bit. You need a lot of computation power to do so, because you cannot do recurrent neural network in parallel. So after that, we have transformer. Transformer, basically, it is some kind of dense neural network, a combination of dense network and convolution network. Okay, we will explain why. So basically, it is faster and it contains a lot of parameters, can try to analyze the text we input. Okay, and one important concept is that when we analyze the text sequence, okay, which input is more important than the other input? As we know, because there are some tokens in the sentence, okay, word in the sentence. When you try to understand the semantic meanings of a of a sentence, okay, you have to divide them into tokens, right? And some tokens are related to other tokens, and some tokens are not related to other tokens. So in order to model such kind of structural relationship, so transformer has a structure called attention. Okay, so let's take a look at this one. Okay, so if we have the input x as an input, so we have several different words, right? We have several different words. And right now, the attention structure looks like, okay, after we obtain the input vectors, okay, and we have a corresponding weight, Q, weight, K, and weight, V. We have three different weights. They are, okay, those weights are different, okay? So we can use the input, okay, that is input, okay? And times, okay, we multiplex those input with these three different vectors. So from the perspective of latent space, okay, originally we have one single latent space, which is X, which is the original token space, right? And we have three different weights. So in this case, now we have three different latent space. Okay, these three different latent space, they may have different meanings, okay, but they are from the input X. Okay, so what is attention? Attention means attention is that after we have such kind of transformation, we have three values. That's Q and K and V. They are query, key, and value. Okay, we have three different vectors right here. Okay, they are from the input, but they have different transformation. WQ, WK, and WV. Okay, so here is a little bit similar to convolution. Okay, we take Q and K, which is query and key. We do matrix multiply pole. It is very similar what we do in convolution. Think about that. We have in convolution we have a kernel, right? We use the kernel to go over the entire image, right? We have a small kernel and we use the small kernel to go over the entire image. And we do such kind of matrix multiplex, right? For convolution, we mentioned it before. We're trying to find certain pattern, which is very, very similar to the kernel. In attention, okay, in transformer, it's very similar. We're trying to figure out if Q and K, they are similar or not. Okay, so after that we have scale, we have softmax, so it's very similar. We want to know which vector in the Q and K, they are very similar. If they are similar, the result of this softmax, the value should be large, right? Should be large. So after that, we use this softmax matrix. Okay, it is a matrix. The value is between 0 and 1. 1 means certain item in the K and Q, they are very similar. So after that, we use this specific softmax value to, again, times with the value V, which means we control how strong the V should output. Okay, so that is the idea. So after that, we have certain output right here. So that is one layer of scale dot product attention. Okay, again, we say it again. Okay, we have an input. We transform them into three different space, which is Q and K and V. And if Q and V, K is very similar, and we output certain matrix. 1 means there are some items in this vector that are very similar. 0 means there are some items in these two vectors that are not similar. And we use this matrix to decide how strong the vector V should output as the final output of this structure called attention. Okay, so think about one thing, but how do we use such kind of attention? Okay, so let's take a look at this figure. It's a very classic bird. Okay, bird. Bird is the name of this model. Okay, so originally we have input right here, and yes, you can see that very similar to Hsiao and the Skitgren. We still need a dictionary. So bird has its own dictionary. It's about thousands of words in this dictionary. But there's also some tokens, special tokens. Okay, so right here we can see CL. CLS stands for class. Okay, although it was used for classification, but like CLS right now, sometimes we use this special token as the first beginning word of a sentence. So as you can see that is the beginning of this sentence. CLS means that. Okay, and we have some ordinary words in the dictionary, right? And of course, we still have padding. If your sentence is very short, so for this model, maybe you need to pad your sentence. Use PAD, this special token. And of course, we have unknown. And that means you have limited dictionary size. So not all English words are in your dictionary. So sometimes for some very professional word, you don't know, you don't have this specific word in the dictionary. So you use unknown token to replace this specific word which is not in the dictionary. Okay, and again we have SEP. That means separate. If your input contains two or more sentences, and you use separate to SEP to separate two sentences. Okay, and we have mask. We will talk about mask later and so on and so forth. Okay, there are a lot of tokens, but we use these tokens more often, and we have ordinary words in the dictionary. Okay, that is the original input. Okay, and after that we have positional embedding. Okay, basically there are some values to indicate which position this word in this sentence. So 0 means the 0 position, 1 means 1, 2 means 2, 3. And there are some other ways to encode the position. Okay, by using positional embedding, we understand where this specific token, for example, dynamic, it is at the end of a sentence or at the beginning of the sentence or middle. Okay, we need such kind of information. Okay, so that is positional embedding. So after that we have segment embedding. Okay, as you can see that to analyze English, since we have limited dictionary size, so not all the word will be included in the dictionary, right? So for example, TensorFlow, it is a new word, so it should not be in the dictionary somehow, right? But as you know, it consists of two words, tensor and flow, and maybe in your dictionary tensor and flow are both in the dictionary. So sometimes you need to do segmentation on your original input. So there is a segmentation structure which can help us to segment words. So the TensorFlow should be segmented into two words. Okay, so in this case we can make our dictionary more smaller. Okay, so that is one way. And after we do such kind of segmentation, the word will be represented as tensor shop and ENSORFLOW, and that is called word pieces. So basically we don't use token to we don't analyze tokens. We analyze the word structure, analyze word pieces. Okay, and even more, if there is some word, again, you know, every word is consist of A, B, C, D, F, G, right? So if the embedding, if the segmentation embedding, they may divide a word into several different small word pieces. If this word is rarely seen and they don't know how to cut it into word pieces, they may use characters to represent the original token if it is a very rarely seen English word. Okay, so that in this case for BERT model, usually we will not, even if we want to analyze new articles, new text, we don't need to add more words in the dictionary, because the segmentation will divide unseen words into word pieces, and they may use single characters to represent the original words. Okay, so that is the segmentation. Okay, so after that we have embedding. Okay, as we mentioned before, there should be some vectors, some weights can convert the original one-hot encoding and positional encoding and segment and to a vector. So when they perform such kind of embedding, okay, to train the vectors, okay, you can see that there is a structure right here. So it's very similar. We have input for each word pieces, and for each word pieces there should be corresponding output. Okay, I write O right here. Okay, output 1, output 2, output N if we have N tokens. And for the first beginning, the first word should be CLS. As mentioned, CLS is the beginning of a sentence. So there is O0, which represent the output of this CLS token, and so on and so forth, and so forth. Unlike recurrent neural network, okay, in the network structure of BERT, basically in this structure, they will have several different layers, right? Those layers are dense layer. That means when we try to, for example, when we try to output O2, basically we will receive the information from the first token, second token, third token, and the last token. So it is unlike recurrent neural network. For the output of cell 2, recurrent neural network only receive the information from the first cell 1 and cell 0. Recurrent neural network cannot observe the input token after this cell. But for attention, for BERT, the output of O2, for example, can observe all the input tokens from and I1, I2 to IN. Okay, so that is the difference. So the network structure of BERT right here is exactly what we mentioned right here. That is the structure. We have several input, okay, and we have the output right here. Okay, so what we should output, it corresponding to these three different values, and all I could show you how it works is right here. Okay, it is the you can find this figure from the network. Okay, so think about one thing. Okay, so first we have the first token A1, second token, third token, and the fourth token. Okay, we use 4 tokens to demonstrate this example. Okay, so as we mentioned that, so in our previous figure, that should be X. Okay, that should be X. Okay, so we have Q, W, Q, W, K, and W, V, right? W, Q, W, K, W, V, K, W, V, W, K, W, V. Okay, for the very first example, okay, we have the original X1, right, and what's corresponding Q1, K1, and V1. And for the later X, they only calculate K value, V value. Okay, so that is the first step. Okay. Next, we use the Q1 right here, Q1, as the first query, right? And we use all the other tokens K, K1, right? K2, K3, and K4. So as you can see that we only use the first tokens Q value as the query value. And we use the rest of the tokens K value as the key value. So in this case, we have 4 different pairs. Q1, K1, Q1, K2, Q1, K3, and Q1, K4. And by product it, okay, we can obtain the alpha value right here. And the alpha value will try to calculate something like a similarity or convolution layer. They try to figure out if Q1 and K1 is similar, or Q1 and K2 is similar or not, and Q1 and K3 is similar or not, and Q1 K4 is similar or not, by using this A value. So there is an alpha 1, 1, 1, 2, 1, 3, and 1, 4. So after that, okay, by referencing the alpha 1, 1, 1, 1, 2, 1, 3, and 1, 4, the value should be between 0 and 1. It corresponding if K1 and Q1 is similar or not. Okay, so if alpha 1, 1 is very large, then that means Q1 and K1 are very similar. Since they are very similar, the output, which is the V1, should be activated. And for example, if Q1 and K2, they are not similar, so the A12 value will be small. And that means we do not activate this V2. So basically, alpha is something like some gate. It will try to activate V1, V2, V3, and V4 correspondingly by using Q1, K1, Q1, K2, Q1, K3, and Q1, K4. So after that, we again output the final value, which is the sum of the V1, V2, V3, and V4 after activation by alpha 1, 1, alpha 1, 2, alpha 1, 3, and alpha 1, 4. So that is B. So the B value will be, that is called self-attention. Okay? The B value will be the self-attention of this input X1. Because in this case, we use X1 as the Q, right? So again, we can further use X2 as Q, and then X3 as Q, X4 as Q. So for each and every input, they have corresponding B value. So that is called self-attention. And that should be a matrix, because we can use X1 as the Q, and X1, X2, X3, X4 as K. And we can further, next step, we use X2 as Q, and the rest of the X as K, and so on and so forth. So there should be a matrix, something like this, right? 1, 2, 3, 4, 1, 2, 3, 4. And that is Q, and that is K. So in this cell, that means we use 1 as Q, and 1 as K, 1 as Q, 2 as K, and so on and so forth. So you can draw a matrix. So that is called attention matrix. So that indicates which token is more important, which means which token is more related to the other token. So if there is some very large value right here, that means the third token and the second token, they have a very high attention value right here. That means after WQ and WK, the second token and the third token, they are similar. So you should output something very strong, very important by using the corresponding V. So that's called attention, okay? So after that, we have attention value, and we can output the corresponding V, right? So we have the output. So in this case, right here, we have almost, I think, 6 layers of attention or 12 layers of attention in this network structure of BERT. So that it can accept a lot of input from from here. And after self-attention, after 6 layers of self-attention, there will be a final output, which is right here, here, and here, and so on and so forth. When they output the corresponding O1, O2, O3 value, they will infer, they will try to, we say, study, or they will try to consult all the other values by using self-attention. So we have attention value, we have the B, alpha value, we have the B value, and we have the output value. So basically, that is the size of this network. So if we have n tokens, for each tokens we have n d dimension, and we have those x will be product with WT, WQ, WQ, WK, and WV. So we assume that the size of the WQ, WK, and WV is a little bit different. But after that, we have QKV. And then we will use this Q and K to perform product to see which item in the Q and K they are similar. So after that, we will have a attention matrix, which is sized by n. So it indicates which token is more related to the other token. So after we have this attention matrix, then we use the V value to output the Z, which is the output. So that is the size of the matrix. Okay. So again, that is another figure, which is again very similar. Okay, we have inputs right here. We have procedural encoding. So here is the attention. So right here we have X, and now we have Q and K and V right here. So after that, here is the output O. And after that, we perform some normalization so we can further pass the information to the next structure. And we will design a FIFO neural network right here and some normalization right here. So that is the actual output of this neural network, of this attention. Attention is only in this part. But for BERT, we have some extra structures to pass the information to the next layer. And as I mentioned, usually there will be 6 layers or 12 layers in this in the structure. And the left hand side is what we call encoder. So you simply just use the X, the token, the word as the input and pass it through 6 different layers of the attention, and including there are some other additional structures right here. So after that, that is the output of the BERT encoder. So if you want to embed your text, you can simply just use the encoder. But in BERT it also demonstrates how the decoder. The decoder is used for some other application like translation. Okay, so if you want to perform a close test, okay, you can simply just use the encoder. But if you want to do translation, you need to input your English words, sentence right here. And here is your, for example, your friend's sentence right here. So the structure is almost the same, But right here, there should be a French dictionary, so that we know what exactly this vector maps to a French word, not English words. Okay, we will talk more deeply about encoder and decoder later next week, but I think that's good enough for you to understand this structure. Okay, so next thing we talk about is that we say that this dot product right here, it's very similar to convolution network, right? Try to figure out Q and K is similar or Q and K is not similar. But think about things. If we have only one set of QK, QV, and we have only one set of WQ, WK, and WV. There's only one way to transform the original X to Q, K, and V, right? So multi-head means we have several different sets of WQ, Q1, WK1, Q1, okay, WV1. Okay, that is one set of W, right? We have another set which is WV2, WK2, WQ2. And we have another set which is WV3, WK3, Q3. That means we have different sets of Q, K, V to perform such kind of self-attention. Okay, that's very similar to the kernel of RNN, as we told before, for the handwriting example, right? We have, I think we have 32 or 64 different kernels in the convolution layer, right? It's very similar. We have several different sets of QKV to represent different situation. Right, so we have different Q and K and V. They have different perspective to analyze the text data. And after that, we concatenate them together and use a linear projection and to perform the output. So basically, we will have this multi-head design. Okay. So again, before we will introduce several TensorFlow example next week. But before we do so, make sure you try Orange. And when you do document embedding, okay, there's another option called multi-language SBIRD. S stands for sentence bird. Okay, this sentence bird can embed a sentence to a single vector. Okay, I think one of the interesting things right here is for this structure. Okay, for this structure, if you would like to do a specific text, for example, close test. If you use this such kind of encoding method, okay, when you do training, okay, you can simply just, for example, remove part of the tokens, okay, and you replace it by mask. And after that, for example, that is 05, right? After 05, okay, 05 is a vector, okay, you can design a neural network right here and output a one-hot vector, which is exactly the same size of your dictionary. So if this SOIL, this word is masked when training, okay, so this network, this bird network, they should use the other words, try to figure out what exactly this word is. So after our 05, okay, there should be a neural network, okay, predefined neural network, and they should output something like, okay, that is in this dictionary, that is the output of soil. And of course, that is for training. For testing, those numbers should be some softmax value. You simply just pick the largest one as the predict word when you do such kind of closed test. Okay, so that is how this model will be trained by using closed test. And of course, there are some other application can be used to train this model. We'll talk about them later next week. Okay, so make sure you train you test a bird in orange. Okay, so for orange, they will, as we mentioned before, if you use word2vec, you will obtain the vector of each word, right? We demonstrate in last hour, right? If you want to represent a sentence, okay, you simply just average all the vectors of these words. But that is not, I mentioned it before, it is not a good design. So for bird, if you want to output the embedding value of this entire sentence, usually we will use this value, which is O0, which is the output of the CLS token, to represent this sentence. Because O0, again, it receives all the information from all the tokens. So usually we'll use O0, which is the output of the CLS, as the embedding of the entire sentence. And we use O1, O2, and O to ON as the output of the individual token. Okay, you can try it in orange. Okay, we'll stop right here. We'll talk more about language model next week.